Hello everyone, welcome to another problem session. So today we are going to talk about something called phase velocity uh, as opposed to group velocity. I find a lot of students really confused about these two concepts. So I want to clarify it. Okay, so for some of the problems that you're going to face that deal with phase velocity and group velocity have to do with when the material through which so light passes. This concept applies to also other waves like sound wave, but we're going to talk in the context of light waves. Okay, so usually when light passes through vacuum, you don't have a kind of a difference in the group velocity and phase velocity, but when it passes through some medium that is dispersive, you are going to have a difference. And so we'll do a problem, for instance this kind of problem that you will find in textbooks and sometimes in contests and exams is so refractive index depends on the wavelength with A and B a constant. So there you can find A and B by doing experiment of which determines n and using different wavelength light, and you plot, and then you can see this is like a intercept and B is like slope if you do this plot. And you can find this is like a one value. I got it from this book. This is a problem from this book, and I just reworded this problem a little bit differently. So then the question becomes is, what is the phase velocity and group velocity if I use this wavelength light? Okay, when I use this wavelength light, what are you going to get? So we're going to do this problem, but first we have to know what is the difference between them. Okay, so to start with, imagine studying a wave that's moving along z-axis, and so the wave equation, and it's some kind of electric field. So let's see, it's really partial difference equation, and that it may be like a x component, a y component. That's the only one that will be non-zero. So electric field pointed in the direction. I'm just going to use as a scalar as E dz square now, because it's going to go along the z direction, equals to 1 over v square d square E dt square. So this is the wave equation, right? And you can see that this wave equation, by just plugging, you can see that the solution is going to be something like E of z t is going to be some E0, this is amplitude, and just say cosine. You can say cosine kz minus omega t, and this k and z are some constant, and if you plug in there, you will see this k and z must be k and omega must be related, like omega over k is going to be equals to the v. And so right now v is just some constant, right? So when you plot this, say you plot this at say t equal to 0, and then if you look at this wave, this is the z direction, like over here, and just a little bit later time, the wave will have moved. So this is at this will be at t equals to delta t. So if you look at if you look at this is the point, and the corresponding points over here. So this has moved delta z in time delta t. So this p has moved to a point p prime. So, and that's because of this part is called phase of this wave, and it's moved, and if you work out, it will see the delta z will be exactly equal to v delta t. So the phase is moving, the wave is moving, and its phase is changing, you know, as time passes, right? It's moving to the right. It's a traveling wave. So this tells you that the interpretation of this is the speed associated with the phase of this wave, and so we call this v is phase velocity. So phase velocity, from the way I constructed it, just omega over k, and sometimes people write v sub p to denote this, just to overkill, but we're not going to do that. We're just going to use v, okay? And when I have to emphasize, I will just v over p. All right, so what is the group velocity then? In order to show that, we're going to have to consider, so for group velocity, we consider two wave. So for group velocity, doesn't depend just two waves, just consider two waves whose omega is a little bit different, just different from each other. Just omega is over here. From there you can tell omega is frequency and k is wave number. So I didn't really write that down earlier, but over here we can have interpretation. K is related with wavelength and lambda is wavelength, and omega is related with frequency. You can see it in some earlier video. We have talked about the waves. So this is the frequency, and this is the angular frequency, and this is wavelength, and this is called wave number. Okay, so we wavelength of omega plus delta omega and k plus delta k. So the one wave is like that, another will be k minus delta k and omega minus delta omega. And we so our light consists of these two waves. So the net, and they have same E0, so E0 cosine plus E0 cosine z minus omega minus delta omega. So you can add these two guys up, or you can add this in the complex notation. So complex notation is very easy to do. So in complex it will be e to the power I k plus delta k z minus omega plus delta omega t plus e0 e to the power I k minus delta k z minus omega minus delta omega t. And so you can definitely take it out. It's common, e to the power I k z minus omega t is this common, and then this will be e to the power I delta k z minus delta omega t plus e to the minus I delta k z minus delta omega t. and this whole thing is simply going to be 2 cosine delta kz minus delta omega t. So this is oscillating part and this is a modulating part. So if you write this out, and the real part of the whole of this will simply becomes, from here take a real part of that, this is going to be 2 times E0 cosine, which is k is the average of the two, right? So cosine k z minus omega t, and then cosine delta kz minus delta omega t. So this is the oscillating, wave at average frequency. Average of these two will be just omega at average frequency and average wave number, and this is kind of modulates it at different positions and different time, modulating part. Okay, so let me erase this and clean up and we'll come back to it. So when you plot it, this wave will be moving in this direction, and you can see that the frequency of this is with the, if you look from here to here, that will the wavelength from this guy. So this distance in terms of wavelength will be lambda will be 2 pi over k, and frequency for that will be omega over 2 pi. So however, this will reach that point based on this envelope. So this envelope is this called this is envelope. It moves as a kind of packet, in a sense. You might say the whole packet is moving, the packet, and so this packet moves at the speed given by this, and that from there, if you look at t and then t plus delta t, so at t plus delta t will be like a little bit, so this packet, say this is a t, okay, then t plus delta t, so t plus delta t, the packet has a little bit shifted to the right. So if you do that study, it will be this packet moves at speed from here delta omega over delta k. These little things over here, they are moving between here to here. They're moving at the speed given by that phase, okay? And this is the modulation part. The modulation part moves with respect to this this argument of cosine, of this cosine. And so so over here the average thing is moving at omega over k. So this is what is called group velocity, velocity of the modulation envelope, or the velocity of the modulation envelope. And this is the speed at which the energy in the waves will move, okay? Now you said, well, you just worked out 2 waves. As a matter of fact, you can work out any number of waves and you will have a concept of group velocity associated with it. For instance, suppose you have laser beam, and it just pulses, and its pulse, and the speed which this pulse moves, that's the group velocity. Now to study a pulse, so what is made up of sum of e I e to the power e j e to the power I k z k I z minus omega I t. So you actually is omega j t. So it's a superposition of many waves can actually be shown to make up this, and each one of these waves have its own. So there are many phase velocities here. So there's one group velocity, but there are many phase velocities. So omega j over kj. So each one is the phase velocities. So if I know, if I go back over here, we have a discrete one. It doesn't have to be discrete. It can be an integral, a continuous. And I'm not going to go there, but suffice to say that if you look at the omega is actually v times k, this is the fundamental relation, and this can be a phase velocity or group velocity depending on this will be a phase velocity, and if I want to do a group velocity, so this is phase, and if I want to do group velocity, I need to take a derivative of this d omega dk, and that will be group velocity. And if this is independent of k, then it will be identical. Take a derivative, it's going to be dv dk times k plus v times 1. So the group velocity and the phase velocity will be different if this is 0. If the group velocity, if the phase velocity does not depend on the wave number, this is, which is same as wavelength, one of the inverses in wavelength. Okay, all right. So now we are ready to do actually some calculation. Now let's relate this to refractive index. So v is speed of light. This is universal speed of light over refractive index. So dv over dk will be equal to minus c over n square dn dk. So this will be equal to c over n minus k times c over n square dn dk. So c over n, 1 minus k over n dn dk. So you can say, let's call this phase velocity now, 1 minus k over n dn dk. So if dn dk is positive, so if for most common materials dn dk is greater than 0, this is positive, this is positive, so Vg will be less than Vp. This is for regular material. If there are some non-regular materials you can construct where this will be negative, and then phase velocity will be exceeded by the group velocity. Okay, so we can use these formulas to actually solve the problem that I posited earlier. So let's look at that problem. Okay, so this is the things we have. So here, when you look at this problem, usually these problems are given in lambda. and the formulas that we worked out is in K, and the relationship is K equals to 2 pi over lambda. And clearly you can convert everything that you have in lambda in terms of K. So instead of going out there like that, I usually just stay in K and convert this n. So the n equals to A plus B over lambda square. That will be A plus B over 4 pi square K square. And now dn over dk can be easily obtained, A plus B over 2 pi square K. All right, so so we need to get so C over n. So we need to get n when lambda is 0.5. So n is A plus B over lambda square. You can just use that there. So A is 1.4 plus B is 0.025 micrometer square. This can be micrometer, and this is half. This is 1 over 4. So that's going to be 1.4 plus 4 times 0.025, which is 1.4 plus 0.1 is 1.5. So that's the refractive index at that wavelength. If the wavelength was different, we're going to get a different refractive index. So the n is already 1.5. So we got n. So we got the n. We need k. So let's k is 2 pi over 0.5 is so 4 pi, and this is going to be micrometer inverse. Okay, dn over dk, no, this a go away, that's wrong, just this is constant, and so dn over dk is going to be B is 0.025 and K is 4 pi, and this is 2 pi square, and so this is micrometer inverse micrometer square. So A is micrometer. So this whole thing is going to be a micrometer. So this is micrometer, and micrometer inverse going to cancel out, and so this is going to be 1 of the pi go away, and so 0.1 over 2 pi micrometer. So we have a k over n. K is 4 pi. So this thing 4 pi, n is 1.5, 0.1 over 2 pi, so 0.2 over 1.5. So this whole thing will be 1 minus 0.2 over 1.5, 1.3 over 1.5. So C over 1.5 times 1.3 over 1.5 is C over 1.73 after calculating this whole thing at the denominator. And from here, C over n, so VP is this guy, so this is VG, and VP is C over n, and C is this 1.5. So this is phase velocity, and this group velocity. Clearly group velocity here is less than the phase velocity. So this is how we can solve some of these problems. Okay, so that was a good example. I'm going to stop here. So you like this kind of thing, you can check out my textbook here. You can subscribe to this channel. I'll see you in another video. Bye.